Okay, this is the fourth and the last lecture in these rapid fire series, um, based on making some notes and trying to share my enthusiasm for this interpretation of quantum mechanics, which is referred to as the Zitterbewegung interpretation. Um, so you've seen this screen already. I added some formulas. I'm gonna walk over them. I'm gonna zoom in on some particular points that may be interesting, and also be very clear in what questions are still open and are not explained, or need further work. I think not further work by me, but by the academics and researchers who are developing this sort of classical interpretation of quantum mechanics. So let me start. What I presented last time was really this idea that you can think of an electron and a proton as a very small superconducting loop. I want to develop that idea a little bit further here by showing what is interesting about these things is that the quantization that comes in and how exactly. As you know, or you don't know, a superconducting loop, a superconducting current, at the macro current, a large one, is actually, a pair of electrons, two electrons with opposite spin that are circulating in, some material. So we don't have that. That's a very big difference. We don't have any material. An electron and a proton, they are there. They are not circulating. The charge inside is not circulating in some kind of material. There is no wire. But we worked that out, these formulas. There is no need for a wire. In a loop like that, a current will generate a magnetic field, and the magnetic field will generate exactly the force that is needed to keep that thing in place. This is what I developed. I'm not going to go very far and develop it all again, but we can calculate the magnitude of the magnetic force using a standard formula for the magnetic field of a ring current. And we know that this force must be, equal to the centripetal force. So that this thing stays in place and doesn't need a wire. The only problem there is a bit like, we said this is a delicate thing. As soon as that electron gets a shock or something, the charge. Because this is the electron, and so we think in terms of a charge inside. Why it's Compton scattering? If you fire photons at an electron, sometimes they will bounce back, scatter elastically, as it's called. The photon that goes out after the adventures it had with the electron will have exactly the same energy or frequency. So that's where the idea of the classical electron radius is there, and it's related to the Compton radius by a defined structure constant alpha. So that's sort of the thing. Let me. I will go back. I started with explaining this superconducting current first, the macro thing. A nice analogy that I did not make is, the superconducting current. This magnetic field. It will be, you can imagine it as something, continuous. I drew here these magnetic field lines. So the field is continuous, but it's quantized, and this is interesting. And this is, this is not a theory, but this is why I think, quantum field theory, which assumes that a field is not continuous, that it's sort of a, virtual field particles. I think that's a totally wrong interpretation of the meaning of a Planck's constant, and it's kind of remarkable that we're now 2023. In 1961, two independent teams, they both got a Nobel Prize in 1961 for proving that superconducting currents come with a quantized field, a magnetic field that is this one actually, n times Planck's quantum of action, h, not h bar, the full one, divided by the charge, the electron charge, the elementary charge, and the surface area of the loop, which, as said, for superconducting currents is quite big, centimeters or larger. If you can create superconducting currents as large as you want, but the field is going to be quantized. Actually, the magnetic flux. I should go probably back to where this formula came from. But the magnetic flux times the charge, times the, my pen is not working anymore. Yeah, no, it's not. Apparently it is a problem. Oh no, there it is. Okay, it's probably because I'm on the command, on these arrows. But so the charge, the elementary unit charge times the magnetic flux is equal to, magnetic flux is the product of the magnetic field vector and the surface through which the surface area of the current that generates that magnetic flux and magnetic force, and that's going to be equal. That's what they found. Always is going to be a multiple of Planck's quantum of action. So the idea that a current, a loop of superconducting current packs, so to speak, a multiple number of Planck's quantum of action, multiple time h. That's actually an idea that is not outrageous, and so we apply it indeed in this Zitterbewegung theory to the two elementary particles that we know that are stable, an electron and a proton. And we derive the electron radius. It's really this. Let me go back to that. You have you can directly derive it from the energy mass energy equivalence relationship, and so for an electron, the energy of an electron is equal to mc square, and it will pack 1 unit of Planck's quantum of action times the frequency. That's the Planck-Einstein relationship. The energy, just like here, is a multiple of Planck's quantum of action and its product with the frequency. So the frequency is basically determined by the energy divided by h bar, or in the case of the proton, we think it's more like it's a ring current as well. But it's probably a spherical thing that comes out of packing models for the nucleus. An electron seems to be, a planar thing with a rather strong magnetic moment. A proton, to get the experimentally measured radius of a proton, which is this one here, 0.841 femtometer. We find that, we need to put a 4 here. And then everything comes out all right. I will talk about the magnetic moment of a proton. There's some the anomaly in it as well. It's quite different from an electron, and that's the factor 4, which you see pop up in the formula for the surface of a sphere as opposed to the circumference, or you also see it pop up as a when sort of volumes are involved, you get a factor 4. And so that's the factor 4. Then, how exactly does it work? I will talk about that a little bit. That's actually one of the remaining difficulties. A ring current, you can modulate it, mathematically as, two oscillators working in tandem, a sine and a cosine, or a similar cyclical function with a phase difference of 90 degrees between the two. I always use this metaphor of a Ducati engine, not a Harley Davidson, but a Ducati engine, where the cylinders are in a 90-degree angle to each other, not like in a Harley 45 degrees. So Ducati has it's a better engine, less friction, less the kinetic and potential energy, the way the pistons move together and translate linear motion into circular motion, orbital motion. It is a very beautiful metaphor. But in a proton, we have if it's spherical, we have like an oscillation in the third, the other degree of freedom that we have in 3D space. We can oscillate along the x-axis, an oscillator along the y-axis, and then a z-axis. For that, we don't have a metaphor from engineering. An engine with two pistons, but then a third piston that comes in on the side. We cannot build a machine like that, but the proton apparently seems to be something like that. Scales, before I go to forces, is you should realize that for the electron, it looks a bit like, almost like a fractal structure, a finite fractal structure, but we have the Bohr radius of an electron that orbits around a nucleus. We have the electron radius itself, the Compton radius. That's, so I said, I talked about scattering experiments. When you fire photons at an atom, they will hit the electron often, or else sometimes they go through. But they will scatter, and then inside we probably have something that is smaller, the Zitterbewegung charge itself, which is like a sort of a hardcore thing, and so we have these three electron radii. The Bohr radius, which roughly is the size of, that gives you the size of a hydrogen atom. That's the same. The Bohr radius of an electron and the size of an atom. And then we have its Compton radius. I often say Compton, but Compton was an American. The Compton radius, and then we have the classical electron radius, which is given by the fine structure constant. All these actually are related. Bohr radius is also related to the Compton radius by this fine structure constant. I will maybe talk about the formula. I put it here. The fine structure constant comes out of classical electromagnetic theory. It's related to the electric permeability and the electric constant and the magnetic constant, the magnetic permittivity, electric permittivity and magnetic permeability. I think that's how they call it, which are related through the speed of light. And then we have a formula which we will use for alpha in terms of mu 0 and epsilon 0. But we will talk about that later. In any case, the thing that you need to remember is indeed that an electron seems to its density mass it's a lot bigger. Even the classical, this is something very weird and that you should remember always, is the classical electron radius. So the what we think of as the elementary charge. It's a unit charge. All of the charges there inside of an electron is about 2.82 femtometer. That's incredibly small, 10 to the power minus 15. But a proton radius is actually even smaller. It's 0. It's less than a femtometer. So that is kind of remarkable in the sense that you know, you must be thinking, and that's what I'm thinking, is that the positive charge and a positron, the Zitterbewegung charge, we have a ring current model for both, is it's a different beast. It's you know, also the unit charge. In an antiproton, we have a negative unit charge. In a proton, we have the positive unit charge. And electrons and positrons, you know, we also have the unit charge, positive or negative. But you know, the structure of an electron and a positron is fundamentally different than the structure of a proton and an antiproton. And I illustrate that here in these, let me go back to them. So I calculate for an electron, you know, the force, the magnetic force. You know, it's the velocity, this tangential velocity. It goes at the speed of light times its momentum. We talked about that. This small Zitterbewegung charge acquires a relativistic mass because it's, you know, it has zero rest mass. That's our theory. It's a charge. Its attributes are only its charge, and then, yeah, I said it has some size. It's not infinitesimally small, like the virtual particles that you have in the Bohr Heisenberg interpretation. You know, for me, something that is infinitesimally small, you know, has zero spatial dimension. You know, well, that thing doesn't exist. Something that exists, I think that's basic philosophy, must have some dimension in space-time or in space. So in that dimension, as said, for an electron is quite large, and it requires an effective mass that we, you know, we assume that it's half of the electron mass. Why? Because you know, this is like a perpetuum mobile. We said you have the ring current generating the magnetic field. The magnetic field make sure that this ring current goes on and that the charge goes round and round and round forever. So we have there, you may compare it to yeah, perpetuum mobile, like on a spring, you will have the energy in the spring and you will have the kinetic energy of the mass on a spring. So it's a bit the same here. We have potential and kinetic energy, you know, sloshing back and forth. And the energy equipartition theorem well tells us that when you have something like that, two different field energy and kinetic energy in this case, you know, half of the energy will be in the will be kinetic and the other half will be potential energy, field energy. So yeah, there's an equivalent mass of the magnetic field, and the kinetic energy of our Zitterbewegung charge you know, makes up for the other half of the total energy. Energy, you can put mc square, but you know, mass, energy are equivalent. So the effective mass, or the energy in the equivalent energy of the effective mass of the Zitterbewegung charge inside of proton, electron, and the proton must be half of the total mass of the electron. So then we divide it by the radius, and that's h bar divided by mc. This is the formula we got here when we directly take the energy mass equivalence formula from Einstein and the Planck-Einstein relationship, plus you know, the formula for a tangential velocity. You know, that's the radius of the oscillation times the frequency of the orbital oscillation. Then you know, we get h divided by mc, and we can calculate that when we fill in the values for the electron mass, and then c to the, let me clean up a little bit. Okay. Yeah, that's all the cleanup I can do. Then you arrive at you know, a huge force. Well, it's 0.106 Newton. And you know, Newton you will think probably in terms of a kg. 1 Newton is a force that gives a mass of 1 kg, an acceleration of 1 meter per second per second. So that's rather enormous at this scale, because here it's a force that would give a mass of about 100 grams, 106 grams to be precise, an acceleration of 1 meter per second. So acceleration is velocity per second. That's enormous. That's huge. We will talk about that. The thing is, when you calculate, and this is interesting, of course, you can say, well, this formula works for a ring current of any size, right? Yes. It's just like at the macro level, a superconducting loop. We can give it a larger or a smaller size. The thing though is that it's going to be quantized, and so this is the quantization basically of the field and also the radius, and the elementary charge. It will depend on how many units of Planck's quantum go in there, and that will determine the radius. But in principle, yeah, you could say I can invent theoretically a new particle, or an unstable one like the neutron. Neutron is not stable outside of the nucleus, and I can fill that in, or a muon electron, and it will work. Well, to some extent, we've done the calculations. The reason why these particles are unstable, according to us, is that they sort of pack a number of a multiple of h bar, but not quite. The oscillation is slightly off, and so that's what makes them fall apart. But the thing is, this model implies that the electron and the positron mass appear as two different constants, and you may say, well. Theoretically, we could build another universe with other stable particles and other values than me and mp, the mass of the proton and the electron mass. Yes, theoretically we can do that, but that's sort of for me not a philosophical problem. We can construct another theoretical universe, but the universe we live in gives us these two values, the electron mass and the proton mass. These are the only two stable elementary particles, plus their antimatter counterpart, of course. All the rest is not stable and is sort of some combination of these two. The charge inside of an electron, I said, which is a weird beast, with a fairly large size, and then what is inside of a proton or an antiproton is much smaller. To go back to the force calculations, is if you take the radius to be the radius of a proton, we can also, of course, we will get a magnetic force that will keep the current going inside of a proton, but we need to add this here, this sphere. It's a spherical oscillation, so there's a factor 4 that comes in when we substitute the radius of our elementary particle for the radius of a proton. So we substitute it by 4 h bar divided by the proton mass, right? And we arrive at again a magnetic force that is equal to the centripetal force, and that force is equal to m square, the mass of the proton squared, c cubed to the power 3 times 4 2 times h bar. Now if you because we have a square here and a proton is so much more massive than an electron, we get, and its radius is much smaller, we get a force of almost 90,000 Newton. Now, if we thought that 106 thousandths of a Newton, 0.106 Newton was an enormous force, and for a proton we get something like 90,000 Newton, you may wonder, like, you are modeling some kind of black hole. This thing can't, you know, such enormous force on such small scale. Really, I said the proton radius itself, and if we think there's a Zitterbewegung charge inside, which must be even smaller than 0.841, this is the measured proton radius. And in a Zitterbewegung model, when we apply it, we get a magnetic force. We get a tiny ring current in this a very small superconducting loop, perpetuum mobile. I said, or a three-dimensional oscillator, whatever mathematical equivalence you want to, or metaphor you want to develop for it, you get an enormous force. And so the first thing you should do is then, of course, check, like, does this make sense? We to sort of show that it makes sense or doesn't make sense. I mean, you're free to judge. We calculated, actually, you know, if there's a formula from general relativity theory, which Schwarzschild, I think that was a German scientist, summarized in 1916 in a very simple formula for a black hole, basically. How much mass, if you have a given, you have a planet or a star, or you have an electron or a proton, you know, when does that thing, when you compress all of its mass in a very, very, very tiny volume, when does that thing become a black hole? And the formula is remarkably simple. I haven't derived it, but I just took it from the web. I'm not a specialist in general relativity theory. Special relativity theory is easy to understand. General relativity theory, I think, is another ball game. But that's the formula. For me, it's kind of natural, general relativity theory. It's sort of you know, an object which is massive, comes sort of with its own space, so to say, and you know, why should that space be a Cartesian three-dimensional space, some kind of yeah, geometry based on a sphere, spherical coordinates, they make a lot more sense, for me at least. But I said I'm not in the formulas. I just have this formula for the Schwarzschild radius. If you would pack the mass of an electron in a very small volume, how small should that volume be before it becomes a black hole? And that's the formula. It's 2 times the gravitational constant g times the mass of your object divided by c squared. And you know, we can be relaxed, because before an electron would be you know, it would have to be of that order, of that scale, 10 to the power minus 57. That's really an awful lot of zeros. 57 zeros. It's smaller than all these small distance scales that you have heard of, the Planck scale, beyond which you know, a physicist says you cannot think that small. The formulas blow up. That Planck scale is about 10 to the power minus 35, I think, or 36. Something like that. But so here we have something that is, you know, beyond that great desert, as Gerard Hooft wrote so wonderfully in his booklet, where he talks about scales and how crazy the world is really at these small scales. But yeah, he talks about the great desert, distance scales that do not make sense anymore, that we can't measure anyway, and so we arrive at a black hole radius for the electron, which is much beyond that. For the proton, is the same thing, and we said we do have a, you know, an enormous force, an enormous magnetic force, an enormous magnetic field, in other words, packed into a very, very tiny small area, 0.841 femtometer. So you may wonder, like, is that a black hole or something? No, it is not, because here also we see that the Schwarzschild radius for something with the mass of a proton you know, before it would be collapse into a black hole and become a singularity, or you know, a lot of other problems that you cannot solve or imagine. Or you know, its black hole radius would be 2.484 and something times 10 to the power minus 54, because it's more massive. You know, yeah, the radius is going to be a bit larger, 1,000 times larger, and the difference between minus 57 and minus 54 as a power is 1,000. So, but still, we are safe. We are not modeling a black hole, and this is where I think you know, this Zitterbewegung theory makes sense. We are going to have something else that makes us think about general relativity theory, and I will come to that now. It's magnetic moment. So the you know, when you go to the Wikipedia page on the Zitterbewegung theory, you basically get a lot of nonsense. They say this model doesn't have any predictive power, cannot be verified. I think it's ridiculous because, you know, everything that we observe and that puzzles us is explained very beautifully by this theory, by the model itself, because you know, once you, the beauty about this thing is that you know, in the mainstream theory, they think of these particles as being point-like indeed, you know, but point-like not in the sense that very, very small, but you know, infinitesimally small. They have no size. And then, you know, you have all kinds of weird theories about, you know, how proton and antiproton annihilate each other and stuff like that. But it's like, hello guys, that happens in some finite space, and you can model with this theory very nicely, you know, how magnetic moments would line up, and how effectively, you know, an opposite electrostatic field vector and magnetic field vectors would actually indeed, you know, if they're opposite, they would annihilate each other. They would neutralize each other, and then you think like, where is the energy going? And that's where then you can think of, you know, yes, some kind of special photon, a virtual photon that you know, takes that energy away. And so for me, the predictive power of this theory is all over the place, in the sense that you know, it gives a common sense understanding, not sort of the hocus pocus of you know, formulas and wave equations that lead nowhere, and for which corrective theories on corrective theories are then being developed to explain something. So, but the magnetic moment, one of the beauties of the thing is that if we imagine indeed an electron to be some kind of a ring current, then we can calculate its magnetic moment. And the formula for a magnetic moment is, I will quickly derive it because we will need it, is the current times the area of the loop, P times A squared. That's the area of the loop. And the current is the current. You know, we have the unit charge, the electron charge, going around at a certain frequency, right, F? So that's the current times P and A squared. So we did that. You get the formula for the magnetic moment, which is beautifully simple. We will get a different formula for the proton because the radius is different. But you get this beautiful formula, okay? And this is then the theoretical magnetic moment. And if you calculate that, you get something like 9.27401, etc., times 10 to the power minus 24. So it's a very tiny magnetic moment, but you should need to realize, again, you know, it's a magnetic moment also at, you know, for something very small. And so that's a rather, you know, this value looks small, but it's rather big if you think of the scale of that ring current. It's a really, really very tiny thing. Now, so the thing is, they in experiments, and this is the beauty, that this shows how powerful technology has become, because we can actually, isolate an electron in a penning trap. It's called a quadrupole magnetic field, and then it goes round and round. I will quickly show that though. Its motion is kind of more complicated than you think with it, and so then you have precession. If you put a ring current, I mean our electron, and you think of it as a ring current, then it will precess, and this precession motion is also quantized. Given by h bar over 2, and but the thing is, with all these complications, precession and the weird trajectory, I mean not weird, it's a beautiful trajectory, but you have like rotations within rotations, and we can measure that. And the funny thing is, and this is the weird thing, is that the measured value is actually a little bit larger than our theoretical value. Now, this is a big mystery for me. I mean, the fact that there is an anomaly, because that's what it's referred to, a small difference between this theoretical value and the actually measured value. Codata is sort of, there's no unique measurement there. Codata and the NIST, the National Institute of Science and Technology of the US, they basically look at various experiments, and based on the weighting of these experiments, they arrive at sort of an official value for various values, like proton mass and energy and all that. These different experiments will yield slightly different values, but the consensus is that out of all these measurement experiments, they've really invested a lot in measuring the magnetic moment of an electron, is that it is slightly larger than the theoretical value. And this is a puzzle, and it's not. I'm gonna move to my screen maybe, where this is an old paper on academia.edu. You can see it here. It's an old paper, and it talks about several things. You can know the reference. One of it is indeed this mass generating mechanism, where we say, like, really is the I can't write on this thing, but really is it is this Zitterbewegung charge, is that rest mass really zero? Is it like photon-like? Our conclusion is it must be, because if we're gonna give it a rest mass, then we're even further away from explaining the anomaly in the magnetic moment, because then to explain the anomaly in the magnetic moment, the fact that the measured value of the electron, or the electron's magnetic moment, is larger than the theoretical value. For that, actually, it's sufficient to assume, as you can see here. Here we exaggerate that the Zitterbewegung charge, the charge inside of an electron, has a radius, so that it's not infinitesimally small, and just a common radius, the radius, the classical electron radius that we know. There is a hard core in an electron from elastic scattering, and so that size is about alpha, and alpha is small, 0.007, so it's less than 1%, but it's sizable. Percent is 1 in 200. It's not and so what you will have is, the theoretical motion that we have here. As you can see, if we assume that Zitterbewegung charge itself is some kind of sphere, we will come back to that, why it might be and probably is a small sphere of charge with zero rest mass indeed. It's a weird thing. It's a philosophical jump you have to make, but it is the one. Matter particles carry charge, and that charge explains their mass, and it's charge in motion. And so the mass of an electron as a whole is really the equivalent mass of the energy in the oscillation, and that includes the kinetic energy of the Zitterbewegung charge and the magnetic field that keeps it spinning around. But you can see that if we look very closely and we assume that that Zitterbewegung charge goes around and around at the speed of light, c, that its center of mass and its geometric center will indeed be on the orbital loop. Will be a position on that circle, but some of the charge is actually outside, and that makes for an effective what I call, we talked about an effective mass. I call this the effective that makes for a small correction in the theoretical radius of our electron. It makes for sort of a slightly larger effective radius, because some of the charge is outlying and will actually, this is the funny thing, the charge that is inside of the orbital loop of its center of charge will be circulating a bit slower than the speed of light, and what is outside of that orbital loop will be speeding at slightly higher speed of light. And so we have that small area in black there, which you can calculate. It's I do that here. But it's I haven't finished the argument is quite complicated, and I'm not good enough at trigonometry, and I didn't find, I had to use like small angle approximations, but I do arrive at roughly something that is in the first approximation, alpha divided by 8, which is very close to that the first order term that comes out of all these weird quantum field theories, first and second order terms in the anomaly of the magnetic moment, because there's some virtual particles which the electron will interact with. That's all nonsense in this mechanical approach. The first approximation you get is alpha divided by 8, and so that it's quite close to let me go back to my notebook, quite close to what's called Schwinger's factor, alpha divided by 2 pi. And so that's good enough for me. In a second order and a third order, you get closer and closer to that value. This value explains about 98.5 or even more percent of the 1% variation. Let me show that here. I said define alpha divided by 2 pi. It's really small. The anomaly in the electron's magnetic moment is 0.11%, so 1 in 2,000. And so from that, we explain easily by this geometric model, 98% of it. So and then I said it's a bit of more trigonometry, and you do a new iteration, and that series should converge, and that's why you have these weird series. But they come out of geometry in our model. So the anomaly in the magnetic moment of an electron, I think, is very well explained in this Zitterbewegung theory, which I said this really goes back to Schrödinger and even earlier. Parson had a ring current model of an electron, and when you look at the Solvay conferences, the great ones, they talk about that, and they say like, as soon as the people understood that the electron has a magnetic moment, they thought of an electron in terms of some tiny ring current, and it works. And I wonder why after the Second World War they didn't do what I'm doing here, because this you won't find this in a textbook. And then you will. I will go back to something very nice in Feynman's lectures, where I think like he must have known all this, But yeah, it's difficult if you're a Nobel Prize winner in physics and you get your prize for a crazy, strange theory in which you yourself may not believe in, but you have to sell it, right? You have to publish, and the weirder your theory, apparently, the more attention you are getting. I'm sorry for being cynical. We've got that for the electron. Where I want to go is for the proton. I said we get a a slightly different formula for the magnetic moment. We still have the current times the surface area of the loop, which we also have here. Actually, this is interesting. For a superconducting magnet, the energy, the magnetic energy, U magnetic here, is indeed going to be, you know, the magnetic moment of that thing. It's like a tiny magnet or a large magnet, because here we're talking these things you see on videos, large currents that keep going and don't radiate their energy away. I said the surface, the charge times the frequency of this Cooper pair times the magnetic force in a loop like that. The formula is NH divided by Q times the surface area. You get NHF. So for the proton, I said N is 4. And we inject these formulas. The frequency is, well, the frequency we can calculate again, you know, saying, okay, this is a tangential speed. This time tangential speed, it is c, but it's a tangential speed of the Zitterbewegung charge inside of our proton. We divide it by the circumference of the loop, so that gives our frequency. It's just the p a square that differs because we have to add a factor 4 here. So we get a factor 4 that is inserted here. Sorry, inserted here. To make a long story short, I can show it to you. The formula that the theoretical, I said this theoretical formula that we had for the to calculate the magnetic moment of an electron, that becomes instead of that now becomes the charge of the proton. And instead of h divided by 2m, we get 2 times h m. So that factor 4, yeah, makes the 2 go upstairs. We can calculate, you know, for consistency of the argument, the magnetic moment in another way, where we say, okay, the frequency, let's use the Planck-Einstein relation rather than, you know, the mechanical calculation of this is the velocity of the charge, and we divide it by the circumference of the loop. No, we can directly use, you know, the Planck-Einstein relation and say, like, the frequency is given by the energy divided by 4 times h bar. Well, this is a frequency, a normal frequency. So if it's not a reduced frequency, then it's h. It's actually important that we're not using a radial frequency here, but a normal frequency, because we have to do then a substitution here. H is equal to 2 pi times h. I said we get the factor 4 here that we get in, and then it also falls into place. We substitute. Well, there's no substitution here. We can scrap, but we have that factor 4 that comes in there. C4mc square. Yeah. Yeah. Okay. The radius is also here. We need an a square, so we get a 4 square factor here, and this 4 factor and this squared 4 factor become just a normal 4 divided by 2, and we get the same theoretical magnetic moment. If we calculate that, there's a funny thing. If you calculate that, you get a value of about 2, a bit more than 2.0203. It's very close to 2, but it's not 2. And then its magnetic moment is smaller. It's minus 26 rather than 24 Joule divided by Tesla. But so again, it's quite significant because, you know, it's smaller, about 100 times smaller than the magnetic moment of an electron. But again, you know, the proton is so much smaller, so it's rather an enormous magnetic moment at such a small scale. Now, the funny thing is, the measured value, we also have a measured value. You know, that's actually, where is it here? The mu codata is 1.41 times 10 to the power minus 26. And you will say, like, whoa, that's way off. your theoretical magnetic moment is, it's not like some digit. It's way off. And this is the funny thing where I think, and I developed that in another paper, which I really recommend reading. Oops. Here on the proton radius nuclear oscillations, I calculate the radius, and the interesting thing here is I actually work a bit backwards. I have another formula for the magnetic moment, which is actually based directly on well, no, I link actually the radius. I have a formula for the radius, which is based on the measured magnetic moment, the Kodata value. And I worked that out, that formula. And the funny thing is, and that's where I realized that something might be missing in the way they work backwards, because in these Kodata experiments they have like a gyromagnetic factor, and there might be a misinterpretation there, because the radius that you get from using the actual Kodata value is 0.703 femtometer, and we know it should be 0.83 or 84, and so that's where there's a square root of 2 that is missing. And my theory is that because indeed we are thinking of a proton being a spherical thing, a ring current, we have an extra direction, and so there must be some precession there. And I explain that by, and also because I have that 4 times, this is a reasoning based on spin numbers, but the precession, if you want to correct for precession, then you're going to have a factor 2, which pops up. And when you apply that one, to this theoretical value that I got, to correct for the precession, because this ring current, when they measure it in a penning trap or wherever, there must be precession, there's an extra rotation, I would say, an extra oscillation. So there must be precession. It's quantized. So if you apply that square root factor 2, you get something that is that's pretty good, 1.428. There is still a difference between 1.41 and my theoretical magnetic moment that I get out of the Zitterbewegung model of about quite 1.26%. So I said the anomaly in the magnetic moment of an electron is really small. And you can explain it by saying that, when you think of a model and a charge that is rotating, some of the charge will actually be outside of the loop, more charge. And so the center of charge, but the charge as a whole, you will have something like that. Now, for us, there's 2 things in the proton. Is first, we do not have what we have for the electron, a measured value that is larger than the theoretical value, I said, which you can explain. But here we have a theoretical value that is larger than the Kodata value. So this one is smaller than that value, and it's smaller by about 1.26%. So that's a problem, and I'm very honest about this. This is really a problem, I think, in this model, where for an electron we can explain the anomaly in terms of geometry. For the proton, that's not so simple, and the only explanation I have, which may sound crazy, is that because of that enormous force, there must be some kind of a gravitational effect. The proton is a very dense mass in a very, very, very small place. And so I think that formula where I showed you, there is no risk. We're not modeling a black hole. It's not gonna, it's not a thing that collapses into itself. Sorry. But the gravitational constant and gravity may or may not, and this is probably where I want to go in the future, is to see if this is realistic, is maybe we should apply, the equations from general relativity and think of, indeed a very dense equivalent of energy that is in the ring current and in the proton, and that's sort of, because it's so massive, it has, it's like a photon that, passing along the sun, it gets deflected. So that energy has an equivalent mass. And so the effective mass of the Zitterbewegung charge, of the unit charge inside of a proton, because it's so massive, it said the effective mass is half the total proton mass. But at such small scale, it may be... there may be a gravitational effect where basically, it gets drawn to the center, not only by the magnetic force, which we modeled. Let me go here. The magnetic force is huge, but maybe there's an extra force, pure gravitation, and that should then explain the deviation we have between the theoretical value of a magnetic moment as we calculated and what is measured. Now, 1.26% first is in large. The second thing is the experimental, the precision in the measurement of the proton's magnetic moment is much less than electron. There have been less experiments. It's also smaller, and so maybe it's not a big thing, but I think it is there, and I think it is something that Zitterbewegung theorists, and there are quite a few of them. I told them, this is something that you probably need to work on, and you need to explain it, because otherwise, there's this element of, this model of yours, is that really making all that much sense? So I've been open about that. I think I have nothing else to say in this lecture, except maybe I thought when jotting some things down, we talked about all these things in another lecture. I like the wave function representation. I said these virtual particles, but there is no need for that. I said I don't exclude that an electron and a positron will annihilate and form. You will have like a zero energy state, both of the Zitterbewegung charge inside of the electron and the positron, and these can then move together in what I call a virtual photon. It carries the charge. That's a real photon does not do that. That's a purely oscillating electromagnetic field. We know that that's a real photon, but this might be a virtual photon and explain neutral currents, what Weinberg came up with, or positive or negative currents, not in terms of a new force, but or a new particle, but yeah, combination. Any case, this is things I talked about yesterday. I saw in my lecture I had one beer too much when talking about that, so I won't do that again. But this is one more formula that I want you to show, and this sometimes is where I go when I read Feynman's 3 volumes of lectures, classical physics, electromagnetic theory, and quantum mechanics, very carefully. I often go back to them, and sometimes I feel like what I'm presenting here is he has these small calculations where I say, well, these are exactly the same thing. It's just, why don't you interpret your calculation as in the way I do? One of the funny things, the nice things he does in volume 2, where sometimes he does already talk about a little bit, how things are quantized. And there's this chapter 28 on electromagnetic mass, and it's a very interesting chapter because Feynman really goes into the depth of what is mass, and the way he develops that chapter is pretty much. I mean, he was a good friend, I think, of Wheeler. In the 50s and 60s. We should, when we think about particles, maybe find some mass without mass model. And where does the mass come from? Then I said the mass is, it's the inertia to a change in the state of motion of charge. And that's enough. It's a metaphysical explanation, but there's no mass generating mechanism that we need, like the Higgs particle or something in this theory. No, we have that charge going around and around and around, and there's energy in that loop, of current and in the field, and that's that energy has an equivalent mass, and that's where mass then comes from. It's not it's like a macro thing. The rest mass of the Zitterbewegung charge is 0, but the electron as a whole, of course, has some mass, some rest mass. And so Feynman has in this chapter here, where he talks about all these things and the nature of mass. And one of the things he says, is maybe, and this is what my theory is about, maybe all mass is electromagnetic in its nature. And I'm going yes. This is this theory. This is the Zitterbewegung theory. All mass ultimately is charge in motion, and the mass comes out of that. It's the equivalent mass of the energy in the motion that's moving. But so the funny thing is, he doesn't go all the way. What he does then is, he says, okay, fine, where does the mass come from an electron? And then he has it's a beautiful mathematically very interesting thing where he does a charge assembly. I don't know if he uses this word. I should look up the lecture again. But he says, let's us assume that an electron is indeed a sphere of charge only, and then we use the formulas for the electrostatic force between all these. We have all of the charge in an electron. Let's suppose it's scattered in tiny bits, infinitesimally small pieces of charge, and we bring them together in an electron. And he does that. And so his formula, it's an integral, which I don't repeat now, but his formula that he arrives at is that if you do that, if you only think about charge, not about mass, and you bring it together, then the electromagnetic energy that you need, to pull all these pieces of charge together from an infinite distance, so from the energy is 0. You see what I mean? You go, you put a charge far away, and then you're gonna bring it to another charge in the center of your coordinate frame or reference frame. So you bring two charges together, and then you can calculate how much energy, potential energy, you need to bring two pieces of charge together. And you're gonna work against the force, because they two like charges, they repel each other. So there's gonna be you quickly arrive at a lot of energy to build what he calls an electron. But what he's building, and it's going to show now, he said, we have this formula, from out of this integral where you bring all your bits of charge together in one big electron, as he calls it, one spherical charge assembly. So you see what I do. I'm doing. All these. It's an argument. I'm doing an integral where I bring tiny, infinitesimally small bits of charge. with zero rest mass, just based on the charge. I bring them together in one sphere, and I have this formula for this sphere. It's going to depend, of course, on, well, because it's a unit charge. You know, we're going to have a formula for the radius, and that formula for the radius is, and this is where it's also funny, and where I think he's like cheating a bit. The radius formula he uses is the classical electron radius. So it's our Zitterbewegung charge. He says he's assembling an electron, but no, he's assembling, you know, the Zitterbewegung charge, actually, because we will see that. He writes this formula down, he derives it, and then he does the substitutions. Okay, this is the classical, well, a classical way, an old way of writing the electron charge. So it's equal to, you know, the electron charge measured in Coulomb times 4 pi's divided by 4 pi's times the electric constant. And then here, and this is the crucial substitution where I'm going like, Feynman, probably, you know, you knew all these things and your theory was probably a realistic theory, but sort of why do you mystify these things? You do a substitution here of your electron radius by a classical electron radius. So this, our E is, what was it in femtometer? 0.8, no, 2.8, 2.8. All right, yeah, that's 2.8, 2.82 femtometer. Sorry for being confused a little bit. These lectures are... it's nice to talk about it because then I know my own theory makes sense or doesn't. Sorry, my pen is acting up. So he doesn't take the 386 femtometer. He takes 2.8 0.2 femtometer. So what he's assembling really is the Zitterbewegung charge. Our charge. You know, or our charge, I mean, you know what I mean. So he does then the substitution, and we know this RE, the classical electron radius, RE, as opposed to the Compton radius, which is equal to h bar divided by mc. You know, we multiply it by the fine structure constant. And I said the fine structure constant, I've done a few papers on that. There's nothing magical about the fine structure constant. It's a dimensionless number that relates so many things in quantum physics, you know, spectrum, color spectrum, because it is indeed, you know, a combination of the electric constant, Planck's quantum of action, and speed of light, and the unit charge. So the fine structure constant is mathematically, you know, a derived constant that we get from this formula. Note it's h, not h bar. So if we substitute, we have a 2 here. I'm making a big mess. Any case, this is the formula for the fine structure constant. So we substitute that. Okay, I can't clean up anymore. Okay, we substitute that here. This formula is here. That's the alpha. No, that's still the same factor we had here. But now we're going to have the alpha times h, the inverse of the, times the electron mass as a whole, times c. So then we substitute alpha. We put this, now we put this here. It's 1 over alpha, so we just switch the denominator and the nominator, times mc divided by h. So our alpha is here, and here we have h bar mec. Now you can see, you know, this all goes away. qa squared, q squared, hc, the h goes. Yeah, and we have what is left. This 1 over 2 factor, which he gets out of his integral. This is really an integration constant. You know, is still there, and he gets that, you know, when you want to assemble all of the charge of an electron into something that is very small, the classical electron radius, then you get this value, and then he sort of rhetorically, jokingly, philosophically, I don't know what, but he says, this is not logical. I only get half of the electron mass, and I had hoped, with this model to explain the mass of an electron in a sort of a mass without mass theory, a model, just by assembling, tiny bits of charge into a unit charge. I should get an energy that is equal to the electron mass c squared. So in other ways, because then you can do, this is energy, U divided by c squared, equivalent mass of that energy, that electromagnetic energy, which divided by c squared, that would be the, how should I put it, the electromagnetic mass. So it's a concept of mass which is based solely in, it's not a measure of inertia, it's based solely on the concept of what is the energy that you get, what is the energy that you need to assemble a sphere of charge. And he says, oh, this is so crazy, and it's not going anywhere because I'm not getting an electromagnetic mass that is equal to the mass of the electron. I'm getting an electromagnetic mass, which is the electron mass divided by 2. You see that? I'm just bringing the c square, but leaving it there. And the thing that I'm going when I read that is, hey, Mr. Feynman, surely you must be joking, right? What you are doing here is you're assembling the Zitterbewegung charge. And then it makes perfect sense, because we said it, the mass of the Zitterbewegung, the effective mass of a Zitterbewegung charge, is the mass of the electron divided by 2. Half of the energy is kinetic, the other half is electromagnetic, is the field. So it makes perfect sense, because your formula then is a very nice mass without mass model that explains, the effective mass. And on top of that, why there's a factor 1/2. There's a ways, I said the energy equipartition theorem gives us the same thing. So you get it from in a number of ways, that factor 2. That was the most interesting when I started studying like physics 10 years ago. Is this 1/2 factor pops up like everywhere, and how can we get rid of it, or where does it come from? It pops up in a variety of contexts, and now I know why, because once you interpret an electron as not something that is infinitesimally small, but that has a physical dimension and has a structure, a ring current structure, then all makes sense. And then I think Feynman must have been joking when he sort of says like, well, look at this beautiful calculation, and it shows so nicely that it doesn't make sense. It does make sense, Mr. Feynman, and I think you've been joking, and probably maybe that was your idea, that the students would get it by themselves, which I think a lot of people clearly didn't, because what I'm presenting here now, I haven't seen that anywhere else. I mean, and I think it makes sense to me. That's why I'm presenting it. That's why I'm putting it on the on YouTube, because I've looked for a long time trying to understand all these formulas, and now I do. But the interpretation is very, very different than the mainstream, what Ehrenfest called der unendliche Bohr-Heisenberg-Wurstmaschinenbetrieb. Where we sort of have wave functions and Darwin corrections and infinities and what have you, while okay, this looks very bad and confused, this whiteboard, but I think it makes a lot of sense in terms of what you, when you're still listening, what you probably want to do, and that is sort of like build the universe, right? Build the universe based on common sense concepts, the minimum set of concepts that you need and not sort of quantum field theory. No, a field can be continuous. What does it mean that it's quantized? Well, that's what it means, you know, that the field, the energy in the field packs, you know, a whole number of Planck's quantum of action, and that there's a force going over a loop. And if we multiply that force times the distance of the loop, which we can write as a wavelength, and times the cycle time, then you know, that will be h bar, or 2h bar, or 3h bar, or whatever, and we have that in an electron and a proton. The remarkable thing is, you know, this is the other question what I had is, so we have an electron and its Planck-Einstein relationship is this one, is E, its energy is h bar times the angular frequency. For a proton, it's 4 times that. Can't we have like particles? Why are there no elementary particles that have like 2 times h bar, or 3 times, or 6 times, or 7 times? Well, the answer there is we have electrons, and we have protons, and we have their antimatter counterpart, and you know, that variety already, you know, of having actually, I would say, 4 elementary particles, the electron and the proton and their antimatter counterpart. You can say these are like the 4 building blocks of the universe, plus of course photons, you know, light particles, which can have any energy, you know, that's continuous. Photons can have any energy. So the Planck-Einstein relationship applies also to photons, but in a different way. But I'm not going to talk about that. They also pack actually always 1 unit. Bosons, this is the only thing that makes sense about the theory of bosons. Bosons pack 1 unit of Planck's quantum of action, always, but can have, because they're linear things. Any case, I'm rambling a little bit. I want to show what you can do with this thing. For me, it is clear how the universe functions, I would say. The essence. This is the thing that philosophers look at. What is the essence of things? For me, the essence is charge. It's not mass. We don't need, I said, we have a mass generating mechanism here. Mass is the equivalent mass of the energy in a charged oscillation, an electron. So mass is, and you can see that with the revision of the 2018-2019, the revision of the system of SI units, which was very interesting, where, you know, what happened there is that a lot of constants in nature have been defined, redefined in terms of other constants of nature. So you have a much more limited set of, you know, variables and physical dimensions. And the interesting thing is the mass unit, kg, is now also defined in terms of Planck's quantum of action, and then combined with the definition of, you know, the distance unit, which you also get out of the you know, the other constant, speed of light, c. And so the kg is no longer, mass is no longer a fundamental unit in the new, I think this is a revolution, and it's a good revolution. All of physics is in the SI units, the way they have been defined now. It's just that they don't come out very clearly, and I suspect that a number of you know, smaller adjustments still have to be made to sort of represent what I present here. You know, I talked about this weird square root factor too, which apparently has not been factored in the Kodata value for the magnetic moment of a proton. Maybe that will come. I write about it in this paper. There's a lot of things that are related to each other. You know, your assumption about the G factor. So the G factor in, if you look at it from the, is, you know, to calculate the G factor, you need to have a theory about the angular momentum. The gyromagnetic factor is the ratio between your angular momentum, a theoretical angular momentum, so that's a mechanical concept, and the magnetic moment, which is an electromagnetic concept. And so you can see that here. The G factor is this factor that you get in an equation. This equation, the elementary charge, which is the same charge as a proton, divided by 2 times the mass, and then the magnetic moment on one side and the angular momentum on the other side, mu and L. That's why I put mu with a subscript L, because you need a concept for your G factor to calculate it. You need a concept, you need to understand what the structure is of your proton. Or when you are calculating the G factor for an electron, which I said we think of as a planar, not a spherical structure, you're gonna have a different G factor. The G factor is one of these things in mainstream theory which should be super simple, but is used sort of as a factor, I think, that confuses people. We get G factors that are like, take on these strange values, 5.58, 569. This is actually the Kodata value of the Kodata calculation of the G factor. You will find that. I wonder, and I looked at it, it's sort of, well, what's your assumption about the structure, about the distribution of mass in a proton? Because, again, when you calculate a G factor like this, you need an assumption that allows you to sort of calculate a theoretical angular momentum, and then you're going to have a theoretical magnetic moment, and then you're going to have a theoretical G factor, and then you're going to have a real one that you can measure based on your angular moment. The only thing you can measure is actually the magnetic moment. You cannot measure, and then the angular momentum, the Kodata value for that is based on a theory that says the angular momentum of a proton should be this. And so because we measured the magnetic moment as that value, we have a G factor that happens to be, this 5.58, 569. And so I did here a theoretical one, but it's sort of, I said, I always get the same thing. The anomaly is about 1.2%. Yeah, that's the one, 1.26%. It pops up in your assumptions of, that you use to calculate the G factor. It pops up in the assumption that you have, on what degrees of freedom there are when the proton has a spherical structure, spherical ring current. How is that going to behave in a penning trap, and all these kind of things. And I think, we need to do more work. And when I say we, it's, I'm very grateful to a few people who opened my eyes, I would say. One is David Hestenes. In the 90s, he really revived this whole theory, this Zitterbewegung interpretation, this classical interpretation of quantum mechanics. And I'm very grateful also to a bunch of Italian researchers, Giorgio Vasallo. I can't thank him enough for showing me that diagram here, this one. This one, where he said, Jean-Louis, you can see it. If we have a ring current and, we're going to add a linear component to the motion, an electron in motion, that's what's going to happen. And the radius is going to get smaller, and, frequencies change. And then you start working with these things, and you see, the wave function means something. It represents an electron. And we can also use it to represent a proton. And so these things then all become very real and explain why, amplitudes or wave functions indeed, can be used to model a probability that changes. Because we don't know the initial conditions of the system, so we don't know where the charge is at a very precise point in time, or when it's going to be at a very precise point in space. So these wave function models the trajectory, at least, and then if you square it, it's like squaring a surface as part of a larger normalization and all that. I'm not going to go into that, but you get a very rational interpretation of all this complicated math, and things fall into place. So going back and finishing and wrapping up, I'm very grateful for those non-mainstream theorists, and I hope their statistics go up. Giorgio Vasallo is a fast rising star. it's very interesting. Also, he's busy with cold fusion, which I don't think we can get net energy out of cold fusion. But when you think about frequencies, there is a theory for cold fusion that makes a lot more sense than unfortunately, some crooks that try to sell different theories. I'm thinking about Mills and a few others. Cold fusion got a bad name. And this hydrino theory also gave a very bad name to people who are doing what I do here, showing like, this and that and makes sense and it's mechanical and you can understand it. But, some people do abuse it to sort of sell you something. Say like, look, I see here some entirely new possibility to create or generate energy. Well, no, I don't. Said these forces are enormous inside of elementary particles, but it's and that's why I think the idea of a nuclear, this is really an electromagnetic force, and it's just like this is the other thing that I found so nice about these Italian scientists is sort of it's like imagine. Just the electric or magnetic dipole moment in a nucleus with a neutron. Sort of think about them as being made up of charge and just being in, some oscillations, some dance with each other, and because of the distance scales, you will get enormous forces that are associated with this nuclear force. But there is no such thing as a nuclear charge. There is electric charge only, and there is electromagnetic force only, and it's the structure of electrons, protons, and a neutron. If you think of a positive and negative charge, it's the structure that determines, indeed a field that is going to appear to be, spatially asymmetric. But its energy conservation is there. All the laws apply. Linear angular momentum are being conserved. There's no magical hat, quantum field theory and quarks, gluons, and whatever. It's just like these are things we will never be able to prove, and they don't make sense. You really think virtual particles are needed to to make this magnetic field work? No, there's no need for an ether. The magnetic field is magnetic field. It's a field is a force without a charge to act upon. That's what a field is, and so fields and charges, these are two concepts that call for each other. A field makes a charge move, and the charge generates the field, and so that's that's not easy to understand, but it's logical and it's simple. Once you sort of take that for granted, that you think differently about what nature actually is, and so that will be it. I will finish. Let's see how long I've been talking. Wow, 1 hour and 1 hour and a half almost. So it's really high time I say goodbye. And probably I will say goodbye, because I must say you've seen that also from some of the lectures. Sometimes you really go like, whoa, maybe this is a bit beyond me to sort of understand. But I don't think so. I encourage you to sort of push very hard on all these things that I've been explaining. Read my papers on ResearchGate. Really, I wrote them not for a journal. So it's all preprints. I write in a very aggressive style, but it's not to make jokes of mainstream theory, which I do, but I also make jokes of myself. And yeah, I put my own theories through the grinder, I think, and yes, you should do the same thing, but read them with an open mind, and if it works for you, then it works for me, and if it doesn't work for you, well, it still works for me, unless you have something, that you say like, Jean-Louis, have you thought about this? And I would go like, oh, but that hasn't happened over the last 5 years. And that's probably why my papers are doing quite well. But yeah, I'm not mainstream, that's for sure. All right, you have a nice day, and I'll see you around on